So our next speaker is Dr. Alon Ben Gal from Gilat Center, from the Agriculture Research Organization. Please. With the title, Irrigation Water Quality Effects on Soils, Crops, and Research Use Efficiencies. Please.
Yes, thank you. I'd like to talk a little bit about research concerning irrigation water quality. I want to give a wide perspective focusing on Israel ARO experience, interests, and strengths around it. I think that'll lead to further discussion about potential collaboration. So not all of Israel's landscape looks like this, but a lot of it does. And the whole country is actually characterized by very low rainfall, high water demand for plants and crops, and scarce water for irrigation. And in spite of that, we've been fairly successful in taking those landscapes in the desert areas and throughout the country and converting them into successful agriculture, including in the most extreme areas. There are a lot of reasons for the success for agriculture in Israel, including in these dry areas. I want to focus just on a couple of the water-related driving principles for success. One of them is intensification, modernization of agricultural systems, meaning the development and adoption of efficient water application technologies. We're mostly talking here about early and full move to pressurized, efficient sprinkler and drip irrigation technologies, and that combined with smart data-driven irrigation scheduling. But also is necessarily the establishment of reliable sources for irrigation. And that's been seen as extensive utilization of non-conventional water. And that's mostly water that's high in salts, especially recycled municipal wastewater that's being used for irrigation. That's the historical move. It's this use of very poor quality water. But recently, the water use and non-conventional water use is more about desalinated water. As Israel has moved to large-scale desalination for municipal drinking water, a lot of that water is having a lot of effects both on our freshwater quality and our recycled wastewater quality. So around half of the water we use in Israel, but historically, is low-quality, high salinity water, characterized in the past by very high concentrations of minerals and contaminants, including salts. And the other half is what we call freshwater, which in the past hasn't been such great quality, but in the past 10, 13 years is becoming more and more influenced by desalinated water, both the freshwater and the effluent water. And all of a sudden we're dealing with water low in minerals, including salts and nutrients. So that's the background. That the issues involving management of irrigation water as a function of its quality, and include as is evident, and I'll continue a little bit on salinity, the effects of salts on soils and crops, secondary effects and costs of leaching those salts, issues surrounding recycled wastewater, long-term effects of irrigation on soils that can be the sodium, the dissolved organic matter, and other things, other contaminants, including nutrients, salts, and pathogens in the water, and what people refer to as contaminants of emerging concern, things that we're recently becoming aware of and being able to have the analytics to discover. There's issues of fertilization and plant nutrition involving interactions and competition in soils and uptake processes when we have nutrients and salts together in our water sources and our soils. And topics around the topic of and the issue of desalination, if that's brine disposal, especially when it's inland desalination of brackish water, issues of excess boron and lack of other minerals that we are used to or like to have in our irrigation water for plants, and secondary effects on the recycled wastewater as the water coming into our water treatment processes becomes much lower in salts and higher quality. We're working in the ARO, and particularly in the Institute for Soil, Water, and the Environment, on all of these issues. Uh, just a couple examples of very recent literature reviews, one by Uri Nakshon about salinity and soils and worldview. Others that I and other colleagues from the ARO have been involved with all in the last year, all published in agricultural water management with different issues and aspects of dealing with water quality and irrigation and agriculture. And one that will be coming out next year that I know some of my German colleagues also are involved with, and other colleagues at the ARO, which will be a white paper about global soil salinity, and should be of great interest and value for us when it comes out next year. A little bit more about salinity. Let's go a little bit deeper about irrigation water salinity. I'm showing here a chart where we see a water balance very simple and a salt balance very simple together. As irrigators, we're mostly interested in quantifying what our transpiration, evaporation, evapotranspiration needs are, and being very exact about giving those and avoiding losses other than that. When there's salts in the irrigation water, though, then the water with the salts flows to the roots. The water's taken up by the roots. Most of the salts aren't. The salts build up on the root surfaces and accumulate. And if we don't wash those salts out, if those salts aren't leached, and in dry areas, rainfall isn't sufficient to leach those salts, then we need to give leaching. So irrigation management becomes not only about ET demands, but about leaching requirements and how do we control the salts in the system. Now, how do we know, how do we approach the questions of how much to irrigate and how much to leach the salts? Well, the approaches are threefold. Experimental approaches with both controlled and field experiments. The modeling approaches to identify and understand mechanisms and evaluate sensitivity to factors of interest and to make predictions about how things will go under different scenarios. And applications based on often on the models to bring the science and understanding to the field and to decision makers. And when we do our best, I think we couple those with economics to really allow decisions to be made correctly. So I'm going to give examples of these very quickly. Here we see some controlled freestanding weighing drainage lysimeters. This enables us to control, isolate variables coming in, variables of irrigation water amount, irrigation water quality, and to close water balances and solute balances, and to be able to really calculate and see the effects of different irrigation management choices or situations on crop growth and on what happens beyond the root zone. Example for bell peppers in a net house on the left, and for olives in freestanding lysimeters in the Gilad Center on the right. Those kind of tools can give us this kind of results. Here we see water production curves for two salinities, a low salinity and a higher salinity for growing bell peppers in a desert area where vegetables are grown. And this just brings home the need for leaching. We see that with the higher salinity, with the crop that's fairly sensitive, we can reach, in this case, the same yields that we reached with the low salinity water, but at a cost of using twice as much water. So half the water is going to leach the salts. We see the same kind of results when we looked at olives, a more tolerant crop, but also to be able to reach maximum yields at any given salinity, we need quite a bit of water to leach those salts. So we're interested in those salts, and we're interested in the water that with the salts, and we're interested in the questions of whether that kind of leaching salts is sustainable. So we're interested on a level looking at consequences of using the low quality water, what happens to that water and what does it carry? In this example, nitrates into the groundwater downstream from intensive agricultural area in the desert. And some other examples from colleagues of that kind of work. We're also interested in sustainability on a larger scale. In the examples of these papers on a national or a global scale, and what does it mean down the line? And today we're more and more interested in the role of desalination. Can it be leveraged to aid sustainability in irrigated agriculture in dry areas? If so, how? What are the costs? The second mode of work is modeling. I bring three examples. One by David Russo and his colleagues, where he's doing numerical stochastic modeling for managing spatial variability and getting to best management practices for use and conjunctive use of variable quality irrigation water sources. Fairly sophisticated modeling, but coming in and making real suggestions for how management should go. Shmulik Friedman and his colleagues, Gregory Kalmanarb in particular, and their work with modeling water uptake for trickle irrigation design, and work that I'm involved with with numerical and analytical mechanistic models based on soil physical properties, water and salt balance, and understood plant response functions in order to predict the response of crops under any given salinity and leaching. The last two of these have been turned into tools that go into the third aspect of how we take the science and make it applicable. The first, Shmulik's work and his model and application DDAS, which is a planning tool for optimized design and scheduling of drip irrigation systems that's downloadable and usable and has people using all over the world, both for understanding processes and for actual design of drip irrigation. And model that an application that I'm been involved with developing that we call ANSWER, a coupled agronomic economic application for decision making regarding irrigation with water as a function of its salinity, where a user can choose crops, can choose soils, and can apply real economic data in our case for Israel, and to predict profit as a function of how much and which water and how much it costs, and it's being used as a decision or making or planning tool by farmers and planners here in Israel. So to round things up, I'd like to make a list of what I see are obvious potential topics for research collaboration between Helmholtz and the ARO Volcani, based on the same kind of concept of experimental modeling and decision support, a triangle. So the first thing would be to look at water flow and solute transport in soil crop systems. Next would be to look better and better understand uptake of water and solutes by plants. The transport and fate of contaminants within our soil and agricultural systems and beyond it in the Vedos zone and into water sources, whether they be groundwater or surface water. The issue of plant nutrition and nutrient management as a function of water source and soil salinity, it's wide open and a lot needs to be learned. A little more specifically would be improving macroscopic water uptake models for cases with combined water and salinity stress, and uptake in plant nutrition, nutrient and water uptake in plant nutrition is a function of irrigation water quality, where we would look at nutrient salt interactions. I think these are all things that we could bring symbiotic skills and interests and tools and work on together. So in the name of ARO Volcani, particularly the Institute of Soil, Water, and Environmental Sciences, and the southern campus of Volcani, the Glingot Research Center where I sit, I thank you and look forward to continuing this discussion. Thank you very much.
Thank you, Dr. Ben Gal.